this is the name of the talk, and I'm here to tell you that your images are too big. Yeah, that's a fact. And if your images are too big, they are slower because they will take more time to load, right? Blurry. We experienced that in e-commerce website, that our photographers complained that our images wasn't that blurry, wasn't that sharp as they shot. And because if you give the browser an image which is larger, it needs to resize it, and it doesn't have much time to resize it. So it can't use an algorithm that is precise and I'd say, yeah, powerful, like Photoshop will do, like, okay? And it's also energy intensive. If you give, yeah, again, CPU needs to do some work, consume more energy, and also has an impact also on the batteries of your users if they are on the phone, or energy, and also on the environment. Carbon footprint will be higher. And they are also more, costly, because if you, I can imagine you use a CDN to deliver your image, the CDN you pay per gigabyte, and so if the images are bigger, they are heavier, and you pay more for them. So in this talk, I want to tell you about how to optimize your images, the size of your images, do it automatically with a tool that I've created, and which does the analysis of your images on your website, does the math to propose the correct image size for you, creates the code for your responsive images, and it also checks that at the many resolutions, the image that gets downloaded is the one that you expected. And what the tool doesn't do is the resize of the images. So the images, you can continue to resize them with the same tool that you're using. If your pipeline, your CI, you have an image server, you do it with Photoshop manually, you can continue to do it like you do it now. So this is me when I was starting getting an interest on web performance. We were at a Google Hackathon on about web performance here in London in 2019, and I'm Andrea from Italy. Andrea Verlicchi is pronounced, if you were thinking about to pronounce it. I made a lot of websites. In fact, I started in 1999 with web development. Then I specialized in front end over the years, and also did some open source projects. The most starred one is Vanilla Lazy Load, which is a JavaScript library to lazy load images. Again, I love images. I'm an images nerd, let's say. And I'm now into web performance for 3 years. For 3 years, I am a web performance engineer. So let's have a refresher. So what? Sorry. During this talk, I will have a refresher for you about responsive images. If you don't remember, we will see how to optimize the loading time of your websites, and do that with an analytical approach. And we'll have, of course, a demo of the tool that I've built. Okay. Now I want to see your hands just to see if you're alive. It's like a button test. Okay, there is also some guy sleeping there. Okay, so raise your hands if you know what responsive images are. If you do responsive images, let's say 50%. Keep your hands up if you know this notation with the X descriptor. Okay, W descriptor, anyone? Okay, picture tag. Still 50%. So you know it all. Okay. So if you do a jump back in time, responsive images were standardized in HTML 5.1 in 2016. So it's quite some time. And this is an image, right? A regular image. I have an image tag with a source attribute and alt width and height, which are the required attributes. And if we add the source set there, it becomes a sort of responsive image. So we can provide the browser two different sources it might want to download, and it can do it depending on that X, which is the density of the display. You know, regular display, retina displays, super retina display. So 1 is for the regular display, 2 is for the retina display, and above. But then we started to do also responsive design, right? So we have big screens, small screens, retina screens, non-retina screens. And so what image size should we serve to those devices, to those viewport widths and sizes? So you will need to scale your images to different sizes and serve the correct size. The correct size, which is, we will refer to it with the ideal intrinsic width. So this is a kind of technical term, but the intrinsic width is the width of the image in physical pixels, okay? So if an image is 1024 pixels, it's 1024, the intrinsic width of the image. The formula to understand what is the best fit for an image on the web is the image width in CSS pixels times the device pixel ratio. So if we have an image which is 300 pixels wide and the ratio is a retina display, the ideal intrinsic width is 600, okay? We can do this. This is the image, and we can provide 3 different sources for the image, each one marked with a W descriptor, which declares this image is, in the first case, 1280 pixels wide in terms of intrinsic width. And then which one will the browser download? It depends on what you specify in the sizes attribute. So in the sizes attribute, you will say, if the screen is at least 40 EM large, then the image is wide, the half of the viewport. So 50 viewport width means the half of the viewport. And in all other cases, the image is wide 100% of the viewport. We need to do that in HTML and not in CSS, because the browser will then parse the HTML and try to figure out as soon as possible which image it needs to download. So this information goes in the HTML, not in the CSS. Another way we could do it is to use the image tag, wrap it in a picture tag, and in the source tag specify a media query. So for example, minimum width 600 pixels. And then if the media query specified in the media attribute is true, then the source set specified in the source tag becomes the new source set attribute for that image. So that's how the picture tag works. And this is the past is over. We are now back in the future. Now this is the future, guys. And in the future, we have this. We don't need to do everything I've just shown. You just can use one single image and put it there. WowP. WowP is the new format of images that will download automatically. Yes, I'm joking. No, this is not the future, guys. This is the present. Yeah. And in the present, we have this HTML that I've shown you. The only thing that changed is that now we can use WebP format. 7 years after. And in the picture tag, same. We have now WebP. Wow. Many changes. If you have friends that work in the W3C, please suggest that we could use one image with many different image formats inside, and maybe we stream only the correct image without specifying anything. Maybe using client hints from the browser to suggest which image to download. But anyway, we have this, and we need to deal with this. So on a slightly different topic, hands up, who knows what are Core Web Vitals? Like a handful. Okay. And so in 2020, Google came out with three indicators that, let's say, help understand how your website is doing. One of them measures the loading time of the web page, and it's called LCP, Largest Contentful Paint, because it measures the time when the largest element on your web page was painted. So if your larger image loads in 2.5 seconds, you have a LCP of 2.5, which is good. It's good under 2.5, and it's bad over 4. Then also not related to this talk, but there are also other two core web vitals. One is the CLS that measures how your layout moves unexpectedly while users trying to interact with it, and the other one is FID, which measures how much time it takes for the browser to respond to the first user input, like a click or a key press. Those three core web vitals are important because they are now part of the search signals for page experience, which means that if you have 3 good values for core web vitals, your page will receive a boost in the page ranking on Google search. That's why SEO are our friends. SEO are friends of Google, of web performance guys like me. They love us because we help improving also SEO. So how can we improve the loading speed, also known as LCP, Largest Contentful Paint? So we could start by improving the server response time, removing all render blocking script, removing all JavaScript triggered UI updates, only the ones that are not triggered by the users, and loading layers that cover everything while it's loading. Remove them, because as soon as you display your content, the better will be your LCP. And we can optimize heavy images, of course. How do we optimize heavy images? So the first thing we can do is to use modern web formats like WebP, AVIF, or JPEG XL, which I don't know if it's already a thing, but it's coming out in the next months, and size them correctly, right? Size them correctly. Let's click on it, and we'll see that we can use we must use responsive images, especially if we do responsive design, which is, I think, the norm nowadays. And that's the point, a focal point. Consider your users' device resolutions and your users' device pixel ratio. Because what we do when we code front end, what we do, we take the designs that our designer passed, and we say, okay, this is, I know, 1440, this is 1980, this is the iPhone, and this is the tablet, and then we design for that. But we don't really optimize for the devices and pixel resolutions that our users have. So now it's time for a quiz. I worked in e-commerce websites, luxury e-commerce websites for 10 years. And the question is, what are the most common screen widths that we found out from our Google Analytics data? Answer A, 1920, 1440, and 375 as the first in order of, let's say, usage. The B is 375, 1920, and 1440, and the C is 375, 414, and 390. Vote now for A. You raised. Okay. 1. Vote now for B. 2, 3, 2, maybe. Okay. C. Wow. Well, the answer is C. Congratulations to most of you. And this is our resolutions. And if you look at them, you will see that most of them are mobile resolutions. Almost all of them are mobile resolutions. Smartphones, from 370 to 428. And the pixel ratio are sometimes 3, sometimes 2, but okay, 2.6, I don't know what's that. Then we have 3 in the topmost, like say, results. We have 3 that are desktop resolutions or tablets in horizontal mode, and only one 768, which is probably a tablet in portrait mode. So, how to optimize for your most common screen widths and pixel ratios? We want to do users-driven optimization. So, given the most common resolutions that your analytics can export for you, with that, we will need manually to do all of these tasks, analyze the image widths at every resolution, and see if we are downloading a too large image. Calculate the optimal intrinsic size. So that will need to be 300 by times blah, 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 do all the math, and choose some of them, because in the end, you will have a lot of possible intrinsic size, but you need to choose some of them because you can't resize your images for every possible resolution. So you need to choose some of them and maybe have 10 variations of them. Produce the HTML tags for your responsive image, which is also not a easy task to do it right. And in the end, test that everything worked when you developed that HTML code. And that's mind-blowing to do manually, right? I did it manually for many of our websites, but then I got sick of doing it manually, and so then I automated it. So in the automator that I'm going to present to you in a few moments, we can analyze the image width automatically. We can calculate optimal image width automatically. We have to do some manual work, which you're not going to like, but yeah, something you need to do, right? Otherwise, we can produce the HTML tag automatically and also test that the intrinsic size download at every resolution is the one that we expect. Bonus points, we can do fidelity capping, which means remember all of those devices with a pixel density higher than 2. They call it super retina liquid mega displays, right? Okay, so Twitter did a study some years ago, and they saw that limiting fidelity for images to 2 times improved latency by 32% with no perceived quality loss. And this tool also allows you to do image capping, fidelity to 2 times. And pages with many images, we just load much faster. Like if you have an e-commerce page with a lot of images, a category page, that will load much faster. So meet now the responsive images automator, which is the tool I've built, which is based on Node.js and Puppeteer. So it runs the browser and makes some measurements and testing also using Puppeteer. Puppeteer is a commander for Chrome. So what it does is 3 things. It extracts the image dimensions from your web pages. It generates the HTML code for responsive images, and it tests, making sure the browser download the image you were expecting. It's now time for the demo, finally. So we want to optimize this web.dev homepage. The image that will cause the LCP, the image that will load for last, here is the pixel image. The other ones are SVG, so this image we want to optimize. And in the detail page, for the case study page, the image that we want to optimize is, of course, that one. Okay, so let's start with the extract part of the automator. So the extract works like that. We have, let me drink because I can't speak anymore. So the extract needs 2 files, 2 configuration files. One is the images, which can be a JSON file or an Excel file if you're not into JSON, and resolutions.json or XLS file. In this demo now, I will show the JSON version for the images and the Excel version for the resolutions, which is what we can export from analytics. Then we pass it to the automator, which will analyze our web page and produce a result, which is, again, a data file in Excel format, which is easy to use and to edit, because we will need to edit it. Okay. And the images JSON file is made like this. We have page URL, which is where it needs to do and analyze our page. The image name, which is just an ID, an indicator, useful for ourselves. The CSS selector, so he knows, the browser knows which image it needs to analyze. We can copy that from the developer tools, right click and copy the CSS selector for the image and paste it here. And the cap22x, which can be true or false, depending on if you want to generate then an image that is capped to 2 with fidelity capped to 2 or not. Optionally, we can also provide an image template, which is a URL with, if you use, for example, they use this ImageX web, it's an image server that resizes the images on the cloud using the parameter you pass in the URL. So if you pass this URL in the configuration of the tool, it will also use it to generate the HTML for you. The resolutions XSL configuration is then just the 3 values: the usage, the viewport width, and the pixel ratio that you exported from your Google Analytics, for example. And then you just run the tool, and the command to run it is npm run extract for the first one. And we have a live demo here. Pretend to coding now, it's recorded. We launch it in the terminal, and it will open up a browser, and the browser will change set the resolutions to many resolutions, and in the end, boom, it produced the results, the what is it called? The data file XSL, okay? The data file XSL is like this. The first 3 columns are just copied from our resolutions. Then we have image width in CSS pixels and the in viewport width, which is another CSS unit. The current intrinsic width, the width of the image that was downloaded at that resolution, and the color is based on, yes, this is optimized, red is this is not optimized. And then you have many numbers here on the right, which are not that important, but the first one is the current render fidelity, the current RTI fidelity ratio, which is the number that more similar to 1 is better. And then in the end, you have the current evaluation, which is a string telling you this image is big, or this image is slightly bigger, or this image is okay. So it gives you an evaluation right away. Last one is the waste, how much we are wasting in terms of percentage and based on the usage. So if the image is wasting a lot of bytes and it's also very used, the resolution is also very used, that will be taken into consideration, and we're wasting 28%. So if we improve the images, we could arrive to 0. Then we have the generate command, which generates the HTML for your images. Again, it takes a data file that we are going to edit in a while and pass it to the automator. The automator will then generate the HTML for each of the images that you configured in the images.json file. So back to it. We also have the, after the vertical line, we have the ideal intrinsic width for the image, which is also calculated with math. And a column which is the chosen intrinsic width, which is the column that we need to write and decide what are the image width that we want. It is already pre-filled with the first rows already green. We need to change the red ones. And then in the right, we have, again, rendered fidelity, rendered to ideal pixel ratio, evaluation, and waste, like we had before, but for related to this column. So this column here is the one that we need to change, because it will generate the images for the resolutions that we will write here. So the green are okay. We have in the evaluation column good or okay, and we need to change the red ones. The first we want to change is 692, and the easiest way to change it is just to copy the value from the leftmost column. And then again, do it also for the other one. And what we see in the end, we only have three variations of the image: 558, 692, and 1116. 16? Yeah. And so we waste only 4% instead of 28% as we had before. And we have also the other tab, which is related to the other image we had in the configuration. We go fast forward. In the end, we have everything green except the last one, which I didn't optimize because the device is not very used. It's 0.80%. It's an old phone. Nobody uses it anymore. So it's okay if the image is slightly bigger. And so it's red. In this page, which is the detail page, we have 5 different resolutions, but it's okay. Then we run the command. We save this file, and we run the command npm run start. Okay, I'll do it in the terminal. What happens is it starts 2 pages, a server with 2 URLs, and in every URL you find the image, which is already resized because it uses the template and the imagex and the code for that image. And also in the other tab, we have the detail page with the code for that image. I know you can read the code, so I did it bigger for you. So this is the code for the home page, which is capped. To cap the image size, the image fidelity, sorry, on the web, the only way we can do it is to use the X descriptor. Because if we use the W descriptor and just pass all the resolutions to the browser, it will download the one that the browser thinks it's better. Instead, if we do like this, we force the browser to use either the 1x or the 2x pixel version of the image, and it's automatically capped to 2. In the main line page, instead, we didn't want to cap, and so it's just a list of sources, and the browser will download which one it prefers. Third step and last one is the test. We want to make sure the browser will download the image that we designed in the data file at the resolutions that we have. So the testing uses Jest, and Jest will then be used with Puppeteer to see that the image size is correct. But instead of writing the test manually, we can generate also the test because we already have the configuration we want in the data file. So I also created a command to generate the test automatically. So we run npm run build test, and it generates the test. As you can see here, I will just write npm run build test, and we then have two different files. I will just format them to make them readable, and we have the resolution, the pixel ratio, so the width, the pixel ratio, and the expected intrinsic width of the image at that resolution. And now, when I run the test, it will open the browser, check every resolution, and see what is the downloaded size for that resolution. So let's do it. Let's run npm run test. We started the server before, because otherwise you cannot test anything, and then run the test, and just will start, and ooh, we have a failure. What's failed? It says, I'm going to read it for you because it's very small, that it was expecting 16,000, and instead, no, it was expected 1242. Instead, it got 16,000 at the resolution, which is 1366, with 1 in the pixel ratio. So we need to fix this test, and first we need to understand what was wrong. So yeah, when viewport width is 1366, the intrinsic width should be 1242. Instead, we got the 1600. So we go to the Excel file and see what's wrong, and this is the line. At this resolution, we told the browser that it should download the 1242, but the resolution is bigger. The ideal intrinsic width is 1366, so it needs the bigger image that we have in our set. So I just save it, regenerates the test, and run the test again. Beep, boop, beep, boop. And now everything is green. So the reason for that is that if you expect the browser to download the image that you want, of course it's not doing like that. It's downloading the image which is bigger than the ideal intrinsic width because it doesn't want the image to look bad, right? Okay, guys, I know it's after lunch. Some of you are really sleeping and I know. But the results are that we got an image weight resolutions, the reduction, by 55% in the listing page, and in the detail page we had 30% resolution reduction in the image weight, and we also reduced the LCP, so the loading time, by 17% and 13%. So this is it. The tool has the easy way to calculate optimal image sizes, the automatically generated code, and the final outcome checked with test. Show me if you're still awake. Raise a hand if you want to give it a try. Okay, you're still awake. Fantastic. So this is the repo on GitHub where you can download it. It's under GitHub Verloc Responsive Images Automator. And if you start it, you can also get, many smartphone raised. It's the first time I see it.
Nice. Awesome.
So to recap, let's wait for the last ones to take the snapshot. Okay, so to recap, we can improve speed, quality, and energy saving of our images with an automated workflow, which will make us save a lot of time and money. And this is it from my side.
Awesome. Thanks, man. All right.